Okay. Hi, everybody. Today's lecture revolves around the Lasso regressing algorithm. We shall discuss three different programs and illustrate for you their specifications and their results. The first program includes the Lasso regressor only, and when it is initialized, we include there or pass the value of the penalty factor which we desire, and at every run of the program we can look at the results of regression and change the value of alpha to drive the results and the values of the coefficients in the required direction. I am sorry. In the second program, we shall use the GridSearchCV class, where we shall use a list of values of the coefficient alpha, the penalty factor, and the class itself will select the most appropriate value of alpha and give you the results of regression. In the third case, we shall use Lasso CV cross-validation function. As I told you, this is the most interesting one. There you pass a list of values of alpha, and the Lasso regressor will select the appropriate value and carry out the necessary regression actions and gives you the results. So let us begin with them one by one. The first program uses only Lasso. So we imported from the linear model of sklearn Lasso as a regressor. Also, of course, as usual, in order to plot, if we want to plot, we use matplot library. We use NumPy because we are going to work with arrays. And of course, the most interesting here and most necessary here is the sklearn library. Here we use the metrics modules in order to measure the quality. Here we imported the R-squared score only. Of course, we can import other metrics upon request. So as a beginning, we used NP-random with a seed 42 so that to guarantee repeatability of randomly generated values, because we use the random generator. The X and Y values are generated as a synthetic data with 100 samples and 3, as you see here, features. Yes. X is the independent variable or the feature. Y is the dependent, and it is given as this formula, which depends on x1 and x2 and x3. And also we added a random component just to make the function more realistic with a portion of noise. As you see here, I have saved the generated X value as a CSV file and call it X underscore Lasso CSV. And also I have saved the Y target as Y Lasso underscore Lasso CSV. These two CSV files will be read by using LabVIEW and will be used there in order to realize integration between Python and between LabVIEW. So we begin our work by initializing Lasso. We call Lasso here. This is the two brackets that present the calling or the constructor. Alpha is given a value 0.1, and this is assigned to an object variable called Lasso. Now this Lasso will be used to fit the X and Y variables. And after fitting, we shall predict the values relative to X only and assign them or save them in a variable called yPredict. Then we printed, after fitting and prediction, we can print the required values, the interesting values by us, which is the Lasso coefficients, the Lasso intercept, and also the score R square value. When we look at them, we find that, as you see here, the R square score is about 0.677, 0.677, which is good. It is not a bad value. And we see the list of the coefficients here. They are 3 because we have 3. This is a linear regressor. We have 3 features. So we have, as you see, 3 components representing the slope for each case. And this is the intercept value. Well, we shall try now to modify this program to be adequate and be used by Python in order to carry out the same regression action by using LabVIEW. So these numbers now, as we supposed, they should be exactly the same as those which we will get in LabVIEW. Okay, so let us modify this algorithm or this program here. The only important thing to remind you with is that you need always to work with functions. The Python node works only by using the nodes, so functions. So we create a function here. It is called the train Lasso. We shall pass to this function the variables X and Y and X test and alpha. Alpha is given directly as 0.01. This X and Y and X test value will be passed to this function from LabVIEW. When I saved them in the previous program here, now they are in the memory, and you can use them by LabVIEW and send them through the Python node to this function here to work with. So now, as you see, we have the values of x and y and x test. They are used here. After that, we can, as you see, initialize the model with a given value of alpha, which is already decided equal to 0.01. And we predict the test component, which is defined by the function train test split function of a scalar, and we find the predicted values, and the other interesting values will be returned by this function. To see these results in LabVIEW, we go to the LabVIEW environment there. I have saved the program there, and we shall have a look at the program and how they work. So it is this function here, this program, I'm sorry. It takes always a few seconds to open LabVIEW. It is opening, as I see. This is the front panel, and this is the block diagram which we have here. This is the node. I want to remind you, this is the node. This is the file path where we saved our Python modified program. This input here includes the value or the array which represents the X features, read delimited spreadsheet VI. This is from LabVIEW, and this is the path to this VI, and this path includes there, the location of the path includes the values which we have saved. X Lasso CSV. Here also we have Y Lasso CSV. I am very sorry. Now we go back. The X value is given, as you see here, as a two-dimensional array. It is directly fed to the Python node. The Y target is reshaped to become one-dimensional and also is fed to the node. And here is the value of alpha. The input side here, as we expect, this is the expected types of values which we will get at the output of the program. We shall have a list or array of the coefficients of the regression, the intercept value, the values of predictions also as an array, and this is the R squared score value. So this is a value, and this is a value, and these two are arrays. You should here include them. They are empty, but we should include them to define the values which will result as the output. At the output, if we look here, this is the output. As you see, this is a cluster, returned values. If I double click it, it is here now in the front panel. So at the front panel, you see the coefficients here, the three coefficients, 1, 2, 3, as we have got in Python. These are the predicted values and this is the R squared score, and this is the intercept. If you remember the values, you find that this value exactly, there it was 0.677, here it is 6.8, it is just approximated. There it was exactly 0.74, here it is 0.74, and these values are exactly the same. So the program works well. We have achieved our goal, and the indicator here at the output of the errors with this green tick gives information, and this green tick shows you that the program is functioning correctly and you have no problems with this program. Okay, so now we go out from LabVIEW and come back to Python to work with. So this is our program which we have worked with. This is the program and the results which we have achieved here. Remember 0.677, there it was 0.68, 0.743, exactly the same. These coefficients were exactly the same. So everything is okay. Now we move to another program where I wanted to demonstrate for you how we can use the GridSearchCV class. Here, the new thing here is you have to furnish to offer the program a list of alpha values, and the GridSearchCV will select the most appropriate one for the Lasso regressor. So as usual, we imported the NumPy, we imported sklearn. From sklearn we imported Lasso, and also in addition to Lasso here we imported GridSearchCV class. Again, we have created the data set. It seems that we have created the same data sets as we did before, 100 samples and 3 features. It is exactly the same data set which I have used in the previous example. Now I have initialized Lasso as Lasso. I have created a dictionary with a key called alpha, and this alpha includes a list of the variables of alpha from which the Lasso will select, the GridSearchCV will select the most appropriate value. So we initialize GridSearchCV, we open brackets and pass there the required information according to the syntax of GridSearchCV. It requires the regressor itself. It is called their estimator. It is here called Lasso. So Lasso is assigned to estimator. Parameter grid is the same. Parameter grid is assigned to parameter grid. The score which we are going to use is R squared. It is assigned to scoring. Cross-validation number is given 5. Concerning the refit equal to true, this is not a must. Here you are asking the program to make use of the selected best value of alpha and to run the program with it. And number of jobs equal to -1, this is required only to guarantee an adequate speed of work of the program, because we use cross validation and it may take time. So here you make available the use of any core which is not working, which is standby in the computer. So this is not a must. So what we have done then, we have initiated the GridSearchCV and assigned it to a variable object called grid. Now this grid will be used to fit X and Y, and we shall get the values from this grid which we want. What I have asked it to do, I have asked it, this grid, to give the best parameters, specifically alpha, so it will give me the best value of alpha which is selected, and I have asked it also to give us the best score. So as you see here, the printing is alpha is equal 0.01. This is exactly the same value which we have found, which we have used in the previous lecture. As I remember, it was used there 0. No, it is not that one. Which I have used here previously is not the best value for this X and Y, but here it is fixed as you see 0.01. This is this value, the first value. There I have used 0.1. Okay. And the score here is very high, as you see, 0.95, which means, of course, the score will be very high because we have selected the best value here by the program, but in the previous lecture, we did not select the best value. So there we have got, instead of 0.98, we have got there 0.77, which is normal, but this is better, of course. Okay, this is the second program. Now we come to the third one, which is the most interesting, where we, okay, this is not that one, here it is, where we shall use the Lasso CV, Lasso cross-validation. Using this algorithm, Lasso, you have to give Lasso CV a set of values. It will select the most appropriate, and then it will run the program with it and give you the results directly. Here in this program, I have managed to import standard scaler to scale the values. The values which are here are the data set, are different than those which I have used in the previous two examples. Here we have 100 samples, but we have 10 features. And we have this value here also. This is the target. As you see, this is exactly the same as we did in the previous example. Here I have saved the value of Y, and I have saved the value of X as CSV files, so that I shall integrate Python with LabVIEW. After that, as usual, we have split the data into training and testing portions with a ratio of 20% for the testing part. Then we initialize the standard scaler as a scalar object here, and we then fitted and applied this scalar to X train. This is the values, the portion which is going to be with used by the regressor. So fit transform X train by X scalar gives you the X train scaled. Concerning the testing values, we do not fit it. We only transform it, as I told you, because it should be unseen for the regressor. So we call the regressor the scalar and transform only the X test and call it now or give it a name variable X test scale. Now we have X train scaled, we have X test scaled, both of them. Of course, X test scaled will be used for prediction and X train scaled with the Y will be used for the regression. So we now before making fitting of the model, we initialize the model. It is Lasso CV, sorry. This is the two brackets, and we pass there the list of values. This is not a dictionary, a list of values of alpha, and we ask the regressor to make cross validations for 5 times. We gave it a name model, and this now model is fitted to the X train, Y train, X train scaled here. We did not scale the Y because we have only one target, no problem. And now we have fitted the model to the data set, and we ask the model to give us the value of the best alpha. It is called here best alpha. So alpha here now is an attribute of the model. We printed it. We also printed the coefficients which result as a result of regression, and we also printed the intercept value. So here is, first of all, the data set which we have. We have 100 samples and 10 features, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is one row, and this repeats for 100 rows. I have just shown a specific number of X5, only 5 rows. 1, 2, 3, 4, 5. And I have shown you also the shape, which is 100 rows and 10 columns. This is the shape of Y, which is only 100 rows and 1 column. And this is the best value of alpha, which is 0.1. These are the predicted coefficients. We have 10 features, so we will have now 10 coefficients: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is interesting here? The interesting here now, as you see, as a result of selection of the best value of alpha, this means the regressors is working very nice. It has shrinked the coefficients so that some of them became equal to 0. This coefficient is 0, and the other one is 0, and the third one, and the 4 coefficients became equal to 0. This means that the Lasso regressor has reduced the number of features from 10 to 6, 1, 2, 3, 4, 5, 6, which minimizes the complexity of the regressor. And again, I can remind you with what I have said before, that the Lasso regressor in this case could be considered as an efficient way of feature management. And the intercept value is here minus 3.8. It is about minus 4. Remember, please, these values 0.1, 0.4, and these are the coefficients. And now we shall move to LabVIEW and to make integration between LabVIEW and Python and see the results there. Okay, so let us go again to LabVIEW and see the results and how it is done, of course. This is our program, which I have built specifically for this. Here are the features 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, I did not show all the rows, but I have given you the size here. It is 100 rows, 10 features as there it is. And here are the paths of the files which I have saved in Python. And here is the output, the cluster output, which results as the output of the node here. This is the node. This is the output. Here is the cluster of the output. And as you see, here is the values which I passed from Python to LabVIEW, and this is the other array which is passed to LabVIEW, and this is the name of the file which was in Python and saved as Python file. This is the number of the Python version 3.6, and I think everything is clear now because I have repeated many times these activities. So as you see here, we got the best alpha is equal to 0.1. There we have got the intercept is about 4. Here it is minus 4.9. It is a little bit different, but really I have checked with the coefficients. I found them very, very close. And also you can guess with me here. This is one of them is equal to 0, the second 0, the third 0, the fourth is 0. So exactly as we have got before, and even this other two, you can consider them equal to 0 because they are very small values, which means that the the features are shrunk to 1, 2, 3, 4, you can say 5 instead of working with 10 features. Okay, now this is okay, and the results are very satisfactory, and now we are working systematically with them, and we know now what to do and how to do all these things. Before finishing with this lecture, I wanted again to go back with you and illustrate with you a specific program which I have designed to demonstrate for you. I want to remind you first with one program which we have worked with in the, I think in the previous lecture, and now I wanted to illustrate what I wanted for you to show you the merits and the importance of using the Python node. I mean by that, why we really do this integration. You may not feel, or we may not feel exactly what I want to tell you, but here is the example which I have worked with you. Here we have this data set, which is in blue, and we have, this is the fitting line, because the regressor is here, ridge regressor, as I remember. Now I have created a new program. Remember these values here, because I have taken the same value. I have tried to create a new program with practically the same values which we have in this program. I mean here, the X array values and the Y array values which were saved here. Now, if I use them, I will get exactly the same, and I have done that for you in the previous lecture. The idea is, why not to use or to create in LabVIEW directly the data set itself, X and Y, and work with it. What we expect and why I didn't do that, and when that thing should be done. Again, let me go back to now to LabVIEW and try to explain to you the essence of this action. Here is the program which I have worked for you now. Let me go and show you the block diagram. This is the block diagram which I have worked out. This is the node. I did not read a CSV file here which represents the X array. Neither I did not read any CSV file here which represents the Y values or the X texting values. I have generated them directly here. So why I did that before? I did that before just to show you that we can save the data which was generated in Python in the computer and read it by LabVIEW and use it by LabVIEW. This is some kind of interface also without the node itself. But really the main reason was so that when I run the LabVIEW program, I can get exactly the same values which I have achieved in Python, so that I can compare between the results and show you that nothing new, and in LabVIEW we work very well. So then you may now understand that we can exactly work directly without writing the values in Python as CSV files, and we have to generate them directly in LabVIEW. Let me work on this issue also. Let me tell you one thing. Here, when we worked with Python, we used the random generator. If we wanted to generate a synthetic data set, and to generate arrays, we usually use random generators. The same thing we do in LabVIEW. In LabVIEW here, this is the random generator, which generates values between 0 and 1, as we do with the random in Python. But the most important thing to know that the basic generator in LabVIEW, though it generates here a set of randomly selected values between 0 and 1, if you run it. If you run the Python, it will give you also another set of random values between 0 and 1, but they will not be exactly the same. This is the problem. So you cannot generate in LabVIEW exactly the same values, 100% exactly the same values as those which are generated in Python. We face this problem only if we want to generate a data set in Python in LabVIEW here, as I am doing here. But let us look at the most important. This is not the most important. I am creating a synthetic data set here in LabVIEW just to demonstrate for you the idea of regression by using Lasso. And we do that the same with Python. But in real life, these features, which represent the independent values, are not generated synthetically or programmatically. They are real values which exist in the real processes, and they must be imported from the real engineering hardware processes to the computer and as features as independent variables. And then in the computer, they will be worked out by using the appropriate algorithms. And now the question arises, if we are working with a real value, real environment, so why not to import these values directly to Python? And preferably we import it with LabVIEW. The answer here is that LabVIEW is the best language, the best environment which ever designed to work as engineering language to interface the real hardware processes with the computer. LabVIEW at the same beginning, when it was created as a data acquisition means which represents how we can transfer data from the real processes to the computer and backwards from the computer to the processes. And the most interesting thing to tell you that LabVIEW as a language, it is a language which was owned by National Instruments. And National Instruments has manufactured many data acquisition boards which are which realize programmatic input-output devices which were installed by use internal to the computer in specific slots or external to the computers. And by using LabVIEW, they were programmed in order to acquire the data from the real processes, and after working out the necessary algorithms there, and in that time the most important was the control algorithms, and after working out this data, manipulating this data with the necessary algorithms, the output is generated also to the ports of the data acquisition boards or the specific boards like NIMyReo, for example, so that it will feed the real process. So shortly speaking, in real life, the features exist in the environment, in the engineering environment, and they must be fed to the computer. And then after working them in the computer, after manipulating them as necessary in the computer, they are fed back to the process. Now, when Python was devised, it was found that Python is more appropriate for data analysis, and it has more and more specific algorithms which are used for processing data. Here comes the importance of integration between Python and between LabVIEW, because now you can use LabVIEW as the excellent engineering language to feed all the independent variables as real values from the environment to the computer. And now you pass these values through the Python node back to Python, where it manipulates them with the necessary algorithms, and then it returns the results back to LabVIEW. Here is the essence of the integration between LabVIEW and between Python. So what I have done here, I have generated a two-dimensional array, and I have really used the same values which were used in the Python. If you go back, you can see that y is equal to 7.7 plus 13 multiplied by the generated x value plus, as you see here, a randomly generated noise. These are the components which were used in LabVIEW, but I cannot guarantee 100% that they are exactly the same as in Python. Why? Because this random generator is not exactly giving exact values as those in Python. They should be different. Anyhow, I have tried my best to make them very close. So this is the generator now, which gives the x two-dimensional values. Now it is fed to the node. And this is the y output. Also, it is a two-dimensional. I have reshaped it to be one-dimensional. Let me write it here. And now this also fed as y. And now I have also generated the test value here is also fed as a one-dimensional array. Now these values which are given to the node, according to the node, now they are passed to Python. And they are worked there in Python. And the output which we get here is given taken from Python. So here the outputs are those values from the Python program which I have shown you before. Now, if you look at the results and the values here, remember the coefficient, the slope, we are talking about a linear regression. The slope of this line is given here 13. There it was 13.4. Exactly the same thing. The intercept here is 4.8. There it was around that. And this, the R there, it was 0.99, so and so. And now it is given here 1. And here is the line, and this is the scatter plot of the data set. Even if you want to change, to calculate the slope 13, you can see here it begins from 5, ends with, let me, 30. 30 minus 5, it gives you 25. The width here is 2, from 0 to 2. 25 by 2, it gives you 12 and a half. Here it is 13. So exactly, it is working and very exact and very accurate, and there is no problems. Please pay attention to this lecture. Try to understand deeply that this Python node is marvelous and very interesting, and that the integration between Python and between LabVIEW is very important issue, especially when it comes to real life, real environment, where we need to input values from the real technological processes to the computer and feed them back to the processes. Really, when using the Python in commerce or in industry, really most of the applications, we use ready files. These ready files are saved in different sites in the net, and they could be important, and I have done that before with many of them in front of you, and they are used as a batch directly, and they're manipulated by using Python also. Okay, I think with this we can say that we understood in a good depth what do we mean by the ridge regressor and what do we mean by the Lasso regressor, the different modifications of both, how we can apply them. And with this, I finish this lecture, and we shall begin another very interesting, very interesting trial to explain to you how we can work directly with LabVIEW without Python, but with using specific VIs, which are a conversion of a high number of scalar functions to LabVIEW done by a group of engineering in France called TDE, Technology de France. This was done 2 years ago, 1.5 years ago. I have an access to it, and I shall explain to you how we shall work with it in the coming lectures. Thank you for listening and wishing you the best. Goodbye.